People are starting to join. Very good. Let's wait another minute so that, yeah. Oh, okay. We are filling up quickly. Okay, let's give it another 30 seconds and then we start. Okay, I can stop sharing the screen. Voila. Okay, so good afternoon, everyone. Welcome to this mini school on the theory of open quantum systems. And although it's December, we won't start a new mini school today. Last week, we decided that, or we convinced gently Graeme to add one more week so that we didn't have to rush through the material. And since December is a particular month and we won't start a new full mini school for the months, it was probably a very good idea to extend the last mini school of November by a week. So it is my pleasure to introduce then the last lecture of Graeme in this course. Yeah, and all of you have probably met Graeme before, so I can keep the introduction very short. Graeme is a NITheP postdoc at UKZN, and he's working with me and with Ilya in our group. Yeah. So Graeme, thank you very much for accepting the offer that I made in public last week to extend the course by a week. I'm very grateful for that. And I think also our participants will be very grateful to hear about another few applications of the Markovian master equation that you introduced over the last couple of weeks. So Graeme, if you would like to start sharing your screen, you're welcome to start with your presentation. Okay, sure. And the usual, please make use of the Q&A facility at the bottom of your screen to ask questions, and Ilya will keep an eye on them and moderate the questions. Yeah? And since we are not so many, we might even have the time to allow people to ask the question in person. So Graeme, I think, yeah, we can see your screen. Maybe you would like to press the play button so that we can see it full screen.
Okay, yeah.
And you are ready to go.
Okay, yeah, well, thank you, Francesco, for the introduction. So, yeah, so hi again, everyone, and welcome back to the 5th lecture in this NITheP Mini School series, an introduction to open quantum systems. So in last week's lecture, we covered a application of the microscopically derived Markovian master equation to describing the interaction between or describing the interaction of matter and a quantized radiation field. So this situation being quite commonly encountered in quantum optics and cavity QED. And so what we basically ended up doing was, for this particular microscopic model, was deriving the corresponding Markovian, deriving the corresponding Markovian master equation. And towards the end of the lecture, we applied this to the example of a decaying two-level system. So in this week's lecture, what we'll do is, yeah.
Have you started scrolling your slides or not yet?
No, not yet. I'm going to skip to the basically the slide that I need to in like, yeah, after I've done the short introduction. Sorry. Yeah. Okay. Oh, no worries. Yeah. So yeah, in this week's lecture, what we'll basically do is just to left off from where we finished in last week's lecture. So going back or looking at the example of a two-level system coupled to a quantized EM field. Okay, so actually, let me just skip to where I need to get to. Yeah, so before we get into this, let me just kind of, again, recap some of, let me just recap some of what we covered in last week's lecture. So the starting point of last week's lecture was to consider the interaction of some bound quantum system, say for example, like an atom or an ion, interacting with a quantized radiation field. So, so for this microscopic model, the total Hamiltonian of the system and environment is given as follows, and where the self-Hamiltonian of the field, so of the environment. sorry, let me just have some water. Ooh. I can't get the lid open on my water. Yeah, sorry. Okay, sorry. Yeah, so the self-Hamiltonian of our radiation field is written as follows, and so it's written in terms of the these creation and annihilation operators B and B dagger. So so B dagger and B basically, when acting on the energy eigenstates of this Hamiltonian, they create and annihilate respectively a photon of wave vector K and polarization lambda in the field. Okay, so at this point we didn't assume anything. We didn't assume any particular properties of our open system S. We only assumed that it has a non-zero electric dipole moment, such that when it's placed in this radiation field, there'll be some interaction between the two. And under the dipole approximation, we assumed that the interaction Hamiltonian of this model can be written in this way, where D is the dipole operator of the system, and E is the electric field operator of the environment. And the electric field operator can be written in terms of the creation and annihilation operators B and B dagger in this way. Okay, so the kind of from this microscopic model, the starting point to obtain the Markovian master equation is to define the Lindblad operators. So these are the eigen operators, or the eigen operators corresponding to the system interaction term appearing in the interaction Hamiltonian. In this case, which is the dipole operator D. So so to begin, we basically decomposed this dipole operator into its corresponding eigenoperators using this definition. And just to recall that in this expression, this sum is taken over terms where this quantity is an operator which projects onto the eigenspace belonging to energy eigenvalue epsilon, where epsilon labels one of the energy eigenvalues of the open system Hamiltonian H of S. So basically what we're doing in this sum is we're summing over these terms where the difference, or we're summing over terms constructed from these projection operators, where the difference between the energy eigenvalues appearing in these projectors has to equal omega, where omega is just some value that we can specify. Okay, so given the fact that the system interaction term, so the dipole operator, can be written in general as a sum of these eigenoperators, the interaction Hamiltonian in the interaction picture can then be written in this way. And what we assumed at this point was that the environment, we assumed that the radiation field, the environment, is initially in thermal equilibrium, such that it's the reduced state of the reduced density matrix of the the environment B can be written in terms of this Gibbs state, where B is the inverse its inverse temperature. Okay, so what we then proceeded to basically just construct the Markovian master equation for this model. So given the fact that the expectation value of using this form of the reduced density matrix of our environment, the expectation value of our we can show that the expectation value of our electric field operator vanishes such that this condition holds. And what this implies is that the master equation, after we make the Born-Markov approximation, but before we make the rotating wave approximation, could be written in this form. And just to again recall that this sum over I and j, so these indices I and j are denote each of the Cartesian components of our dipole operator and electric field vector. So I and j can either be x, y, or z. Okay, so so to then write this in the form of the Markovian master equation, we then have to evaluate these quantities gamma, which are defined as the one-sided Fourier transform of our reservoir correlation functions. So for this example, or for this microscopic model, our reservoir correlation functions are formed using each of the Cartesian components of our electric field vector, so E, I, and EJ, where just to reiterate that the time dependence of each of these operators is generated through the interaction picture transformation. Okay, so when we looked at evaluating this one-sided Fourier transform, we noted that because our environment Hamiltonian H of B commutes with the reduced density matrix of our environment at the initial time, we can show that these reservoir correlation functions are time homogeneous in that the dependence on T, that there is no explicit dependence, or our reservoir correlation functions have no explicit dependence on T, but only on the time difference S. So you can just rewrite using this, we can rewrite our reservoir correlation functions in the following form. So this helps slightly simplify the evaluation of this one-sided Fourier transform. Okay, so then what we basically did was to evaluate these quantities gamma. So just basically plugging in each of the components of our electric field, or I should say first transforming this component into the interaction picture, and then just plugging this into this expectation value, we can show that these one-sided Fourier transforms can be written in terms of expectation values which are quadratic in these creation and annihilation operators, so B and B dagger. And well, the way that we then proceeded was to note that because our environment is, we're assuming that our environment is initially in thermal equilibrium at some temperature or inverse temperature beta, then these expectation values can be evaluated using these following identities, where so basically the expectation values containing at least two either creation and annihilation operators vanish, and the only non-zero components are the expectation values containing only a single creation and annihilation operator. And where, just to again recall that this n defines a Planck distribution. So this gives the average number of photons occupying a mode of the field of frequency omega k. And you can see this explicitly depends on the inverse temperature of our field beta. Okay, so just kind of skipping out a few technical details, what you can do is just substitute these identities into this expression and then take the continuum limit. So convert the sum over k into an integral, a three-dimensional integral taken in k space. So kind of just skipping out some of these technical details, what you can show is that the one-sided Fourier transforms can be written in this way, and we can then further reduce this expression by exploiting this formula. And when we do this, we can then introduce the well, this allows us to then decompose our one-sided Fourier transform into its Hermitian and anti-Hermitian parts. So defining, introducing these gamma and S coefficients that we talked about when we went through the microscopic derivation of the Markovian master equation. So for this example, so in the most general case, these gamma and S quantities, or this gamma quantity defines a positive semi-definite matrix, and this S quantity defines a Hermitian matrix. But for this case, what we can show is that, well, we can just introduce these as kind of single coefficients rather than matrices, or you can equivalently interpret these as well, because of this dependence on the Kronecker delta, you can interpret these as matrices which are diagonal and whose diagonal elements just contain the same entries. So for this example, this gamma, so a gamma coefficient can be written in terms of the Planck distribution evaluated at frequency omega, and this S quantity can be or just is written in this way. And so when we decompose this, if you can recall that when we decompose this matrix into its Hermitian and anti-Hermitian parts, then this allows us to express our master equation in GKSL form. So by doing this, what we did is ended up with the quantum optical master equation. So this is the Markovian master equation for the microscopic model of a open system coupled to a quantized EM field taken under the Bohr, Markov, and rotating wave approximations. So just to kind of recall, or just to kind of clarify some of the terms in this master equation. So if you can remember this first term, this unitary term contains, which depends on this quantity S, contains the Lamb shift contribution. So this basically just generates a renormalization of the energy levels of our open system due to its coupling to the environment. So this contains our Lamb and Stark shifts. Whereas this second term, which is called the dissipator, generates our non-unit. So this corresponds to a non-unitary evolution. And for this example, so for this particular microscopic model, the dissipator is written in this form. So the way that you can, so let me quickly just go back to the previous slide. So the way that you can obtain this quantum optical master equation from this master equation here is you can, well, after we substitute in this gamma into this expression, what we then do is we can, what we firstly assume is that this sum over omega is taken over both real and positive values of omega, both positive and negative values of omega. So what we can then do is to separate this sum explicitly into its positive and negative frequency components. Okay, so you can see here, okay, yeah, so then what we can then do is we can exploit the property of the Planck distribution. So the Planck distribution basically satisfies this property. And then what we can do is we can then use this to show that that the gammas appearing in this dissipator satisfy these two, or satisfy, or can be written as follows for when when omega is either positive or negative. Okay, so then what you can also do is that in this sum containing the sum which is taken over negative omega, is that we can note this following property, is that each of the system eigenoperators with frequency omega minus omega is equal to its adjoint for positive omega. So you can basically just when you just put all this together, you can basically just you can rewrite the dissipator of the quantum optical master equation in this form. So this hopefully clarifies how you can get this expression. So the reason that it's useful to rewrite it, the dissipator of our quantum optical master equation in this form, is because it allows us to, well, we can see that we basically broken up the dissipator into two terms. So the first term, so the term this term basically describes thermally induced spontaneous emission in our open system, whereas the second term describes thermally induced absorption processes. And so these thermally induced spontaneous emission rates are given by gamma are given by this quantity, and the thermally induced absorption rates are given by this coefficient. So the gammas corresponding to positive and negative omega respectively. Okay, so I think that where we basically got to last time was, or where we basically finished up last time was applying this to the example of a two-level system. So I'll maybe just skip some of these technical details, but basically we assume that our open system has only two possible states, so a ground and excited state, which we label G and E, and we assume that the Hamiltonian of our open system can be written as follows. So we basically assume that the eigenstates of the Pauli Z operator, or sigma 3 in this case, are the energy eigenstates of our system Hamiltonian. Okay, so for this example, we can then explicitly calculate the Lindblad operators in our Markovian master equation. So these system eigenoperators. So the way that we do that is that we just recall this expression that we had, and the way that we can then explicitly calculate these Lindblad operators is by just essentially substituting in, or it's just constructing the projectors which project onto the eigenspace belonging to energy eigenvalues epsilon and epsilon prime. So for this example, because we only have we have a two-level system, our system Hamiltonian only has two energy eigenvalues, which correspond to minus omega 0/2 and plus omega 0/2. So what we can then, so given that so what we can then do is we can see for this example is that because we only have two energy eigenvalues, there are only 4 different possible combinations of epsilon and epsilon prime that we can substitute into this expression to generate our system eigenoperators. So we can have either, epsilon is equal to plus or minus omega 0/2, and epsilon prime is equal to plus or minus omega 0/2. Okay, so basically just by using this, we can then just substitute in these projection operators. So the projection the operator which projects onto the eigenspace with energy eigenvalue minus omega 0/2 is just the projector onto the ground state of our two-level system, whereas the operator projecting onto the eigenspace with eigenvalue plus omega 0/2 is just a projector onto the excited state of our system. Okay, so what we can do is we can just substitute that into the right-hand side of this expression, and we can then determine that there are only 3 different possible Lindblad operators that we can generate. So if we basically just substitute epsilon prime and epsilon are either plus or minus omega 0/2, then we basically get 3 Lindblad operators which are of this form, and which we generate using these projection operators. Okay, and then the way that we can then evaluate each of these the way that we can then evaluate each of these expressions is by noting that for our two-level system, the dipole operator, so our system interaction term, which is the dipole operator appearing here, will be will just be a 2x2 matrix. And using arguments from the theory of light matter interactions, you can argue that this dipole operator has vanishing diagonal elements. So therefore, this dipole operator will only have will only contain off-diagonal matrix elements. And for this reason, what we can then do is we can define the off-diagonal elements of our dipole operator can be defined in the following way. So where this just gives us the transition matrix, the transition transition matrix element, or the transition dipole moment describing the transition between our ground and excited state. Okay, so yeah, basically this dipole operator will be a 2x2 matrix with off-diagonal elements given by D and D and its complex conjugate. Since this is a Hermitian operator, its off-diagonal elements have to be related through complex conjugation. Okay, and because again, because our dipole operator only contains off-diagonal elements, this can then be expressed just in terms of these Pauli raising and lowering operators. So the Pauli raising operator sigma plus is just defined in this way, and the Pauli lowering operator is defined in this way. So the reason that these are called lowering and raising operators is that when we apply them to the energy eigenstates of our system Hamiltonian, they either increase the energy of our system by an amount omega naught. So the raising operator increases the energy of our system by an amount omega naught, whereas the lowering operator decreases the energy of our system by an amount minus omega naught. Or, well, it decreases the energy by amount omega naught, not minus omega naught. Okay, so basically what you can then do is just, using this, you can just express the dipole operator in this way. So just in terms of these Pauli raising and lowering operators. And so by then just substituting this expression for the dipole operator into each of these system eigenoperators, we can then basically just obtain explicit expressions for each of our Lindblad operators. Okay, so basically putting this into these expressions, we can show there are only two non-vanishing Lindblad operators. So the Lindblad operator corresponding to omega is equal to omega naught is quite easy to verify that this is just zero. Whereas these two, so the only two non-zero Lindblad operators are given by A omega naught and A minus omega naught. So yeah, you can show for this case there are only two Lindblad operators, which are proportional to these Pauli raising and lowering operators. Okay, and then where we basically finished up was that we just if you just substitute, so now that we have these Lindblad operators, we can just substitute these into the quantum optical master equation. And if you do this, if we just, for simplicity, neglect any contribution that's made through the Lamb and Stark shift, so we assume that that S is approximately zero, so that's negligible, then what we end up with is the quantum optical master equation that we obtain for this two-level system case is just written in this form. And where for simplicity we've just so this row just still gives us, we just suppressed the S label on this on the reduced density matrix row. So this still is so this is just a master equation for the reduced density matrix row S, but we just remove the S label for simplicity. Okay, and where we also introduce these gamma naught quantities. So gamma naught basically gives us the spontaneous emission rate of our two-level system at 0 temperature. So the way that you can kind of show, or the way that you can verify this, is by noting that in the 0 temperature limit. So when we assume that our radiation field is initially in the vacuum state, so when there are initially no photons present in the radiation field, then this Planck distribution n will just vanish and be 0, and then so this second term will just be 0 in the 0 temperature case, and what we'll end up with is just we'll just end up with a single term in our dissipator with a rate given by gamma naught. So this, as just to again mention, that this just gives us the spontaneous emission rate of our two-level system at 0 temperature. And so when we have in the finite temperature case, we have thermally induced emission and absorption processes occurring at rates gamma naught n+1 and gamma naught n respectively, where in this case n is just n is the Planck distribution evaluated at the transition frequency of our system, so omega naught. And for convenience, what we can do is define a total transition rate, which is just the sum of the emission and absorption rates. So this is just given as gamma naught 2n+1. Okay, so I think this is where we kind of ended up last time. So what I want to do for the remainder of this lecture is just basically was to carry on with this example, but specifically look at solving solving the quantum optical master equation for this two-level system case. Okay, so the way that we can go about doing this is by noting that when we're dealing with a two-level system, the state of our two-level system can be always written in the following form, where this this vector here is so this is a 3-vector containing each of the Pauli operators sigma x, sigma y, and sigma z, and this is a 3-vector which is given as the expectation value of this, or it's just given here, and this is what's referred to as the Bloch vector. So I'm assuming that most of you are already familiar with the concept of the Bloch sphere. So yeah, just to kind of mention that in the essentially what the Bloch vector defines is a 3-vector whose modulus is always less than or equal to 1. So in the case where the case where the modulus of our Bloch vector is equal to 1, then this just basically describes the case where the reduced density matrix of our system describes a pure state. So in this way, the state of our two-level system can be mapped to a single, could be uniquely mapped to a single point on our Bloch sphere, which lies on the surface of the Bloch sphere, in the case where the modulus of V is equal to 1. In the case where the modulus of V is less than 1, then this describes a case where the reduced density matrix represents a mixed state. And in this case, the state of our two-level system can be represented by a point which lies within the surface of the Bloch sphere. Okay, so just to kind of what we can also, so just using this kind of general expression, we can note that the reduced density matrix of our two-level system can be completely expressed in terms of the expectation values of our Pauli Z operators, so sigma 3, and the expectation values of our lowering and raising operators, sigma minus and sigma plus. So so in this expression, the populations of our two-level system as a function of time can be just described in terms of the expectation value of the Pauli Z operator. So the diagonal elements of this density matrix give us the populations of both the excited and ground state of our two-level system as a function of time. So this matrix element here gives us the excited state population, whereas this matrix element here gives us the ground state population. And the off-diagonal elements of our reduced density matrix give us the coherences of our state. So for this example, our coherences the time dependence of our coherences can just be expressed in terms of the expectation value of our lowering and raising operators. Okay, so the way that we can then use this, well, we can now use this to basically to attain a solution to this master equation. So the way that we can do that is by essentially just taking the time derivative of this expression and then plugging it into the left-hand side of this equation. And also what we can do is then just also plug rho into the right-hand side of this equation. So what we can then note is that on the left-hand side of this equation, we'll just have a 2x2 matrix containing the derivatives of terms in this matrix. And similarly, on the right-hand side, we'll have another 2x2 matrix depending on whose matrix elements will be written in terms of these Pauli operators. So then what we can do is we can generate a set of equations of motion in terms of the expectation of our Pauli operators, the expectation values of our Pauli operators, by basically equating matrix elements on both sides of this equation. Okay, so when you do that, you then basically, you can, or by also exploiting some of the algebra of the Pauli matrices, what you can then show is that you can, that what this master equation, or what you can do is use this master equation to derive the following set of equations of motion for the expectation values of our Pauli X, Pauli Y, and Pauli Z operators. Okay, so by then solving these equations of motion, we can then basically come up with a complete description of the time evolution of our two-level system due to its coupling to the radiation field. So just to recall here that this gamma is the total emission rate. So it describes both. It's the emission rate describing both thermally induced spontaneous emission and absorption, and where this gamma naught is just is the emission rate at zero temperature. Okay, so these equations, since these are just linear differential equations, and because they're also uncoupled, they're fairly straightforward to solve. So, for example, you can solve them just using the Laplace transform technique. And by doing so, what you can then show is that, well, I've provided some, for the case where our two-level system is initially in its ground state, so where the reduced density matrix of our two-level system at time t equals to 0 is just given in this form. So for this initial condition, what you can show is that the solution to the expectation value of the Pauli Z operator of this equation is just given as follows, where for convenience this is expressed in terms of the it's expressed in terms of its stationary state. So this stationary state here can just be obtained by setting the left-hand side of this third equation to 0 and then just solving for the expectation value of sigma z. Okay, and you can kind of straightforwardly verify that its steady state solution is just equal to this. It's just equal to this expression. Similarly, as well, we can also obtain. So if we denote the population of the excited state, so if we denote this matrix element of our reduced density matrix as P of E, so the population of our excited states, a function of time, can be shown to be given as follows. So where again this is expressed also in terms of the steady state population of the. So this solution is expressed in terms of the steady state population of our excited state, which well, you can use the, well, you can basically just use the steady, you can use this expression for the steady state of sigma z, and then just substitute it into this expression here to basically show that this gives us the steady state population of our excited state. Okay, so on this slide, what I've basically done is just given a kind of few simple plots that just kind of qualitatively describe how our two-level system evolves in time, which are obtained from these solutions. So so if we just focus, so we can first focus on this first plot at the top of this slide. So so what I've plotted here is basically the expectation value of the Pauli Z operator as a function of time in the case where our two-level system is initially in its ground state, and where where n, so the Planck distribution evaluated at the transition frequency of our two-level system is, I've just chosen the case where n is equal to 2. Okay, so so yeah, just to clarify what's shown on this plot. So what we have, so what this blue line represents is the solution obtained from just directly numerically integrating our master equation. And what these what these orange points represent is these points plot is the solution, is the analytical solution obtained from this expression. So what you can, this is a quite simple case, but what you can see is that these two clearly agree with each other. So yeah, so just to kind of qualitatively describe what's going on here. So initially our two-level system is in its ground state. And then as what happens over time is that we have a monotonic increase in, so the expectations value of Pauli Z monotonically increases in time, and then it eventually plateaus at some value which is approximately, in this case, equal to minus 0.2, which, so this just provides the steady state value of the expectation value of sigma z. So so yeah, this just basically, so this steady state value is just equal to this. So so yeah, so what basically happens is that or what shall I say is that what you can basically verify is that the analytical solution that's obtained from this expression, or I should say the steady state solution, exactly corresponds to the, or actually, let me reword this. So the state of our system. So what this expression implies is that the state of our system, so the steady state of our system, will, in the limit that t goes to infinity, will eventually be described as will eventually be given as, can be represented in terms of a thermal equilibrium state. So basically the steady state of our two-level system can be, will be exactly equal to the thermal equilibrium state. So its steady state will be in the form of e to the minus I beta h of s, as you would kind of expect from a kind of standard thermodynamic analysis. Okay, so this is this first plot kind of describes can be used to describe the time-dependent behavior of the populations of our two-level system, when we assume that our two-level system is initially in its ground state. So what the second plot here provides us with is so this just plots the expectation value of sigma x this time as a function of time. And what I've done here is I've shown the case where our two-level system is initially, so rather than being prepared in its ground state, is when it's prepared as initially in a coherent superposition state. So as a superposition of, so when our two-level system is in a superposition of its ground and excited state. And for this case, what you can show is that the analytical solution of sigma z is just given here. So it just describes a simple kind of exponential decay occurring at rate minus gamma over 2. And you can quite easily also show that its steady state expectation value is just 0. So what basically happens here is that, so for this example, so I should also say again that this blue line just gives again the solution obtained from numerically integrating the master equation, whereas these orange points give the, just plot this analytical solution. Okay, so in this case, so for this case, when our system is initially in a coherent superposition state, what this plot tells us is that what happens is that it's any coherences that are initially present in the system basically decay exponentially in time, considering the fact that so the expectation value of Pauli Z basically gives a measure of the coherences in our system. So basically, when our off-diagonal elements are non-zero, the expectation value of Pauli Z will be 0. And when there are no coherences present in our system, so when the off-diagonal elements of our reduced density matrix are 0, then the expectation of Pauli X will be 0. So what this plot tells us is that as a function of time, any coherences that are initially in the system just decay to 0. And in the steady state, our system has no coherences present. So for this example, so this plot basically just gives us a kind of example of decoherence, where any coherences that are initially present in our system are destroyed due to the interaction with the environment. Okay, so I think that's hopefully clear what these two plots show for this case. Okay, so we can kind of consider a slightly more. So what we basically looked at is the case where we just have a two-level system spontaneously emitting into a thermal reservoir. So what we can do is also look at a slightly more elaborate example where we still have a two-level system, but one which is where the atomic transition E to G is now driven by an external single mode field on resonance. So the way that we can describe this example is by basically modifying the Hamiltonian of our microscopic model by introducing an extra term. So so for a two-level system which is driven by a monochromatic driving field, the Hamiltonian describing the interaction of our system with this driving mode in the interaction picture and within the dipole approximation can be written as follows, where again this operator is just the dipole operator of our two-level system in the interaction picture, and this operator is the electric field strength of our driving field, and this can be written as follows, where what we're assuming a monochromatic field has only a single frequency component, which is on resonant with the transition frequency of our open system, so at frequency omega naught. And where in this expression, these epsilon vectors are the polarization vectors of the field. And so just substituting this into this Hamiltonian, and similarly substituting in our dipole operator, which, if you recall, can be written in terms of these Pauli raising and lowering operators. What we can then show is that, or what we can then do is that we can basically make the rotating wave approximation. So we neglect any terms any rapidly oscillating terms which oscillate at frequency e to the I oscillate at frequency 2 omega naught or minus 2 omega naught. So when we do this, we can basically show that this Hamiltonian describing the driving of our two-level system can be written in this form, where this capital omega defines the Rabi frequency. So this is just equal to the it's equal to the dot product between the dipole transition moment of this transition with the polarization vector of our field. Okay, so just without loss of generality, we also assume this to be real. But, okay, so the way that we can then, so for this example where we now have a driven two-level system, we can kind of phenomenologically include this driving into our quantum optical master equation. So since this Hamiltonian only depends on operators of our system, so these Pauli raising and lowering operators, we can expect that in the master equation, this will only generate a unitary time evolution. So the way that we can kind of phenomenologically include this is by just adding a term to our quantum optical master equation, which is of this form. So because it's, because this is just a commutator of this Hamiltonian in the interaction picture with our reduced density operator, we can then, this then implies that this just generates an extra unitary time evolution, along with the non-unitary evolution, which is described in terms of this our dissipator. Okay. So yes. So what we can then do is we can then go back to we can just perform the same procedure that I showed in the case where we just had in the case where we only had a spontaneous emitting two-level system, i.e. the case where there was no driving. So what we can then do is that we can write the reduced density matrix of our system in terms of it will just be a 2x2 matrix, which we can write again in terms of the expectation values of our Pauli Z, our Pauli Z operators, and the lowering rate and the Pauli raising and lowering operators. So if you just do this for this example, what you can show is that the set of equations that you can generate are given as follows. So where this, these are just three-dimensional column vectors, and this G defines a 3x3 matrix with these matrix elements, and where this B is also just a 3 vector, which is given as follows. So these equations that you can generate, these equations of motion for the expectation value of our Pauli X, Y, and Z operators coincide with what are in the literature referred to as the Maxwell-Bloch equations, or the optical Bloch equations. So what so if you're already maybe slightly familiar with quantum optics, what the optical Bloch equations describe is essentially the microscopic model what we have here. So what they describe is the time-dependent behavior of a two-level system, of a damped-driven two-level system. Okay, so what we can do is that, again, I'm kind of skipping out some technical details here, but if we basically solve these, equations of motion, again, using, for example, like a Laplace transform technique, we can basically, we can obtain analytical solutions which describe the time-dependent behavior of the excited and ground states, as well as the coherences. So what this plot shows here is just it shows the time-dependent behavior of the excited state of our two-level system for different values of the driving strength, and for an environment which is initially at 0 temperature, so which is initially in its vacuum state. So as you can kind of see here, what this plot does is it interpolates between the kind of the weakly driven case and the strongly driven case. So what this this kind of dashed dotted line represents is the weakly driven case. So you can see here what happens is that we only have a kind of or the time dependent behavior is similar to that in the case where we have is only slightly modified from that in the case where we have no drive. So what we have is again a kind of a monotonic increase in the population of our excited state. Or I should again say that we're assuming that our two-level system is initially prepared in its ground state. So what we have here is like a kind of monotonic increase in the population of our excited state, but which then, as a function of time, reaches its steady state value, or quite rapidly reaches its steady state value. So as what happens is we increase the driving strength. So as we go to this kind of dashed line, what we can see is the kind of appearance of these like Rabi oscillations, which are overlaid on this kind of monotonic increase in the population. And when we go to the strong driving limit, you can just see that we basically have more, we have a kind of more pronounced Rabi oscillations. So as you increase the driving strength, the system basically takes longer to reach its steady state, as you would maybe kind of expect. Okay, as well, I haven't listed them here, but you can, for this case as well, obtain analytical values for the steady states of the excited state population, as well as the expectation values of the Pauli sigma x, sigma y, and sigma z operators. Okay, so based on how much time we have left, I probably won't really go into this, but what you can also do is look at the for this example is to look at the kind of spectrum of the fluorescence spectrum of the radiation emitted from the radiation. Yeah, so the fluorescence spectrum of the emitted radiation in the steady state. So again, I won't really go into the kind of details of this, but what basically happens is that yeah, so basically yeah, so what this spectrum basically describes is the well, it's basically you can calculate this spectrum from basically the Fourier transform of the expectation values of the Pauli operators. But again, I won't really go into much detail about this, but basically what happens is that you can show that as you kind of increase the driving strength, then you have this kind of qualitative change in the behavior of the spectrum as you go to stronger and stronger driving strength. So at kind of weak driving strengths is that the spectrum basically will just be a kind of simple Lorentzian. And then what happens is that when you go to the strong driving limit, you get the appearance of where you have a kind of single central Lorentzian, but you also get the appearance of these two sidebands, which are located at frequencies omega plus, so omega naught plus capital omega, where capital omega is the Rabi frequency, and omega naught minus omega, capital omega. So this is what's called a Mallow triplet. And so you can basically, from these optical Bloch equations that you can derive, you can basically show that you get the appearance of this Mallow triplet. So this was kind of theoretically predicted by Mallow in 1969, and then was later experimentally verified. Okay. So we have maybe a couple of minutes left. So hopefully everything that I've kind of mentioned so far has been clear. So in the kind of last couple of minutes, what I'll maybe do is just quickly touch upon another application of the quantum optical master equation. So for this case, what we can consider is the example where our open system is given as it's just a simple harmonic oscillator. So in this case, the Hamiltonian of our open system can just be expressed as follows, where omega naught defines the natural frequency of our system. And again, if we just assume a kind of an interaction Hamiltonian which is of this form, then what we can do is we can to obtain the quantum optical master equation for this example, we can then proceed to, as we did before, just decompose our system interaction term into its corresponding eigenoperators. And again, these eigenoperators then give us the Limberlad operators appearing in our quantum optical master equation. So in this case, if we just assume a kind of, we assume that these interaction terms, so the environment interaction terms appearing in our interaction Hamiltonian are the same as the previous case, but in this case, we now we assume that our system interaction terms are now just given in terms of these creation annihilate, or in terms of these A and A dagger operators of our system. Okay, so basically what you can then do is that, again, I'm kind of skipping through some technical details here, but what you can do is to then show for this type of interaction is that the corresponding the master equation for a damped harmonic oscillator in the Schrödinger picture can be written as follows. So here you can just see that for this case that our Limberlad operators are given by A and A dagger. So yeah, so I should basically say that okay, well these A and A dagger define the creation and annihilation operators for the of our system. So well, if we for the case where we're dealing with a damped harmonic oscillator, our system, or the Hamiltonian of our system, is equivalent to that of a single bosonic mode, where these A and A dagger are the annihilation and creation operators for this mode. And so in this case, our Lindblad operators are just given in terms of these creation and annihilation operators, and where again we have these transition rates occurring, which are as the same as in the previous example. So we have a term in our dissipator which describes the thermally induced spontaneous emission of our harmonic oscillator, and then we have a second term in the dissipator that describes the thermally induced absorption processes. And you can we can see that this, as we previously discussed, that this Markovian master equation is in GKSL form. Okay, this essentially what this line basically expresses, is that this is in GKSL form. Okay, and then just to again reiterate that this n is just the Planck distribution evaluated at the natural frequency of our open system, omega naught, and this gives us the mean number of quanta in a mode with frequency omega naught in the environment. Okay, so if we basically label if we donate the nth oscillator eigenstate of this number operator by n, so by this I mean we can denote a state n which satisfies this relation, and where n basically, so here n are the Fock states, so these are the states which are labeled according to the number of quanta within this mode, or this mode of our system. Then what we can do is we can use this master equation to derive a closed equation of motion for the populations of the nth energy level of our open system. So as I kind of already mentioned, is that, well, given that these eigenstates define or the set of these eigenstates define a basis on our open system Hilbert space, then we can express the reduced density matrix of our open system within this basis. And in this way, what we can do is we can then note that the diagonal elements of our reduced density matrix rho s will give us the populations of each matrix element will give us the populations of each of the energy levels of our system. So and the off-diagonal elements will give us again the coherences. So what we can do is we can define the populations of the nth energy level in the following way. So it's just obtained by sandwiching rho s between the nth energy. Yeah.
There is a question, and I assume it's related to the previous math equation. And the question is, can you get stimulated emission using GKLS?
So this master equation?
No, I assume that stimulated emission, I don't know in which case, but I mean, yeah, can you get stimulated emission?
So yes, I think that, so let me just go back to this. This master equation. So yes, so yes, what this basically this first term describes the spontaneous emission processes that occur as a result of vacuum fluctuations in your environment, as well as thermal fluctuations, right? So basically, when we have an environment which is initially at some fixed temperature T, then what this first term describes in our master equation is the stimulated emission due to these thermal fluctuations, right? So yes, that's what the master equation does describe, stimulated emission. Or were they also talking about the driven case, or were they just talking about this case?
I don't know if the person who is asking question want to clarify it. They can ask again with clarification.
Okay. Well, I hope hopefully that answer clarifies things, but yeah, just feel free to ask another question if it doesn't. Okay, so yeah, okay, yeah, just to kind of just to kind of wrap up now. So what we have for the damped harmonic oscillator, we have we have what our quantum optical master equation is a Markovian master equation in this GKSL form, and what we can do using this master equation is to derive a closed equation of motion for the population of the nth energy level of our system. So if you basically just for the master equation on the previous slide, if you just sandwich both sides of this equation using these eigenstates, what you can show is that this just gives us this equation of motion for the populations of our nth energy level. So this is what's referred to as the Pauli master equation, and you can see here that basically what it describes is basically what the Pauli master equation describes is the rate of change of the population of the nth energy level, and we can see that this Pauli equation only connects the adjacent energy levels to the nth energy level. So you can see that on the right hand side we only have a dependence on the also the equation of motion of Pn only depends on Pn plus 1 and Pn minus 1. So kind of intuitively what this describes is basically that we have basically a kind of spontaneous emission that occurs as a result of as a result of our system interacting with its environment. So basically what this first term basically represents is emission processes which brings our system from an energy level n plus 1 into the state n. And similarly, this kind of second term basically describes absorption processes which bring our system from a energy level n minus 1 into energy level n. Okay, and then what we can also do, like similarly to what we did in the case of a two-level system, we can basically solve this equation, and what you can basically show is that the steady state solution of this Pauli equation can be expressed in the following way. And so it can just be written in terms of the Planck distribution evaluated at omega naught. And so basically what you can then do is if you just substitute in the expression for the Planck distribution into here, what you can do is rewrite this stationary solution in this form. So what you can recognize here is that this stationary solution is just the Boltzmann distribution of our system taken over the energy eigenstates, just taken over the energy eigenstates of the oscillator n. So what this implies is that in the limit that t goes to infinity, what happens is that our harmonic oscillator eventually reaches eventually comes into thermal equilibrium with its environment. Again, so this is something that you would just expect from a kind of standard thermodynamic analysis, is that eventually our system and environment will, after they're kind of, or when they interact, as we let t go to infinity, they will eventually come into thermal equilibrium. Okay, I think this is basically where I wanted to kind of leave it. So yeah, so what this slide does is it just basically gives a kind of brief overview of some of the approximations and assumptions that went into the microscopic derivation of the Markovian master equation. So namely, we assume the weak coupling limit, as well as you make some separation of timescales arguments, so which correspond to the Markov approximation or rotating wave approximation. Okay, so I think that's okay. Maybe that's probably time's now up, but what I kind of wanted just to mention is that what we've basically talked about in these lectures is a description of the Markovian dynamics of open systems. But what you can also do is look at kind of non-Markovian descriptions, where you can drop some of the assumptions that we made when we basically perform the derivation of the microscopic Markovian master equation. So there are kind of many situations. So even though there are situations where this kind of the quantum Markovian master equation gives a relatively accurate description of your open system dynamics, there are also many situations where it kind of fails to give an accurate description due to the breakdown of these the approximations that went into its derivation. So namely the Bohr Markov and rotating wave approximation. So this can happen in cases where where our system couples strongly to its environment, and where you have entanglement and correlation initial states in finite reservoirs. So there are also kind of other techniques which are kind of beyond what we've done here, that allow you to kind of derive some types of master equations that apply to the description of non-Markovian dynamics. Okay, so this is basically the end, I think, now. So yeah, thank you. Hopefully what I gave was a fairly understandable lecture. But yeah, if you have any questions, then please just feel free to ask.
Yeah, Graeme, thank you very much for this very comprehensive review of Markovian quantum master equation and description of open quantum system. And your last slide is probably a preview of what we could do next year. Yeah, maybe a mini school on non-Markovian open quantum systems. We had probably a few questions already. Ilya, do you know if there are more questions, or is anyone raising the hand and would like to pose a final comment?
So far, I don't see any more questions.
Okay. And Graeme, maybe let me ask a question quickly. Maybe to give people maybe some seconds to formulate the question. Graeme, you mainly focused on analytical approaches. Yeah? Do you have any advice to our participants in case the problem they encounter requires some numerical approach?
Yes. So. Well, it depends on. So I assume you're also talking about. So when you want to describe Markovian open system dynamics, right?
Yes.
Yeah.
Let's keep the non-Markovian for another school.
Yeah. So yeah, there's depending on what type of systems you're interested in, there's a variety of numerical approaches. So. Off the top of my head, probably one of the most kind of commonly used approaches for the kind of numerical simulation of Markovian open system dynamics using Markovian master equations is the kind of the use of the kind of quantum trajectories and the unraveling of the master equation into kind of pure state trajectories. So this is a kind of approach which is very common, what is most commonly used in kind of quantum optics. So is that, I think, what you want? I'm not sure if that's
that's
so,
possible.
So yeah, but
it could also be the topic of another mini school.
Yeah. So I should just say, yeah, that I mean this. So yeah, these kind of approaches are the quantum trajectories approach is just one of the. It's just one example of a kind of stochastic description that you can. So yeah, as kind of Francesco said, what we've done here is we basically kind of we've just described the dynamics of our open system kind of by just solving our master equation analytically and then kind of plotting the solutions. But you can kind of also, there's a whole literature of ways in which you can kind of simulate the master equation stochastically rather than solving analytically. So if you're kind of interested in this, I'll shamelessly point you towards Francesco's book, Theory of Open Quantum Systems, where there's a whole chapter which basically talks about the kind of stochastic description of Markovian system dynamics using Markovian master equations. Yeah.
Okay. Thank you.
But also just feel free to email me if you're interested in this as well.
Thank you for that. Yeah. Ilya, did someone raise the hand?
There is a question from Camille, and Camille asked, maybe Graeme can talk a little bit about steady states.
Okay.
Maybe I can let Camille talk and he can tell us what he meant by this question.
Yes, maybe that's easier. Yeah.
Hi, Graeme. Hi.
Hi.
Can you hear me?
Yeah, I can hear you.
No, maybe you could, talk a little bit of steady state. So, in which condition we have steady state I mean, maybe not fully to talk about that because this might take long, but just because steady states, I mean, as you know, depending which application you are looking at, is the main things that people are looking at. So, so yeah, just maybe mention that their steady states are not always unique in the.
Yeah, so there are, off the top of my head, I'm not sure if there's.
Or better, if there are general results about steady states, or things like that.
Yeah, so for at least for master equations which are of GKSL form, then there are general results for steady state. So basically, you can show that the so maybe if I go back a bit, depending on how far. I'm not sure what's the best. So maybe this master equation. So basically, yeah. So yeah, I mean, correct me if I'm wrong. I mean, but I as far as I know, that there are general statements that you can make about the steady states obtained from this this kind of general form of the Markovian master equation, right? And basically, what you can show is that the steady state solution of this master equation is unique and is basically given in the form of the thermal equilibrium state. So it's basically the Gibbs state defined with respect to the Hamiltonian of your open system, I think. And this relies on there, and the way that I think you can show this. So there are certain conditions that you can show. I mean, I can't remember off the top of my head, but there are basically certain, I think it's called the KM, I'm not sure, maybe you can remind me of this, Camille, but I think it's called something like the KMS or something like that condition, where basically you can basically use this to show that this property, that the steady state solutions are just the thermal states, right?
Yeah. It's I mean, yeah, I'm also, I mean, yeah. So what I remember is you have like a general results saying that. So maybe it's a bit technical, but if the jump operators, so you have the jump operators join all the level, all the energy level of your system, then you can show that you have a unique steady state, which is given by the Gibbs state of I mean, which is the thermal state at the bath temperature. And in case one or several levels are not affected by the jump operator, then you can have multiple steady.
Okay, yeah. Okay, but I have. Yeah. We are getting now quite technical, and since it's already a little bit late, we can make a note of this kind of questions and consider them in a further mini school next year. Yeah, I think that would be probably much better instead of confusing our participants at the end. Okay. So Graeme, thank you very much for the nice, very nice lecture series. Yeah, and Ilya, thank you for moderating the questions. Camille, thank you for the questions, and thank you to the participants that have been for us for 5 weeks. Yeah, so thank you very much to everyone. I hope you all enjoyed the concept of the mini school, and we will continue again next year, and probably since January is probably a half holiday months, we might start the next mini school in February. So thank you very much, everyone. Graeme, again, thank you very much. And as usual, we will put the talk online just now. And I wish you all the best, and looking forward to see you for the next mini school again. Thank you very much. Bye everyone. Bye Graeme. Bye Ilya. Thank you very much.
Thank you. Bye.
Bye.